welcome back. So we're talking about the divergence, the gradient, and the curl of vector fields. These are vector calculus operations. And in the last two lectures, I covered the grad and div. So today we're going to talk about the curl of our vector field. And curl is a really useful quantity. It tells us how much our vector field is rotating. So these were the two vector fields I looked at in the last lecture for divergence, where this one is diverging, and this one has divergence 0. But we noticed, if we just look at this one by eye, this is kind of symmetrically outsourcing in the radial direction. There's no rotation to this vector field. So what we hope is that this curl quantity will be 0 for this case. And in this vector field, which had divergence 0, we notice that our flow essentially is just rotating objects. And so we would expect that we would have a non-zero curl for this case. So I'm going to define the curl, show you how to compute it. We're going to look at it for these two examples. And we'll think about some other kind of applications of the curl in fluid flows and in things like solid body rotations of like asteroids and mechanical objects. OK, good. So the curl of a vector field is essentially this differential operator del cross product. And remember, I'm just going to write down the del operator. So del, or nabla, whatever this differential operator here. And since we're doing a cross product, I'm actually going to write this in 3 dimensions. Before, I've been usually doing this in 2D just for simplicity. Here, I'm going to write this in 3D as partial partial x, partial partial y, and partial partial z or z. OK, that's my del operator. And we're going to take the cross product of del with a vector valued function f. So f bar is going to be a function that has 3 components, f1, f2, and f3. And just to be very explicit, because this is a vector valued function of 3 components, it's a component of x, y, and z. These are functions of x, y, and z. X, y, and z, or z, x, y, and z, x, y, and z. OK, so that's my vector valued function. And just like these are 2-dimensional vector fields, this would be a 3-dimensional vector field. It would describe how vectors are pointing in all of 3 space. And this could be a nonlinear function. This f1, f2, and f3 could be nonlinear functions of x, y, and z. So for example, I could have a vector field that does something here and does something totally different over here based on this nonlinear function. And so the curl of f, the way we write this is sometimes the curl of f. So curl of f is equal to the cross product of my del operator with my f vector. OK, so cross product of this vector with this vector. And so we would literally do the normal cross product that we're used to seeing. So this is equal to the determinant. So I'm just going to write down like the determinant of this 3x3 matrix that has an I, a j, and a k component. So this is how we do the cross product, just remember from high school. We take the determinant of the ijk unit vectors. The second row is my first vector, which in this case is del. So partial partial x, partial partial y, and partial partial z or z. And the third component of this curl of this determinant matrix we're writing down is my f function here, f1, f2, and f3. And so you can actually compute this and write this out. If you have these f components, you can compute the determinant of this matrix, and it is an expression that will have an I, a j, and a k component. So this is really important. The curl takes in a vector field, f bar, a multi-component vector field, and it spits out another vector field. It will have an I, a j, and a k component. So it takes in a vector, and it outputs a vector. Now that's different than the div and grad operators. So grad takes in a scalar and returns a vector. Div takes in a vector and returns a scalar. And curl takes in a vector and returns a vector. And so this is kind of interesting, actually, if you think about why these are the 3 kind of primitive linear differential operators that we use for all of linear partial differential equations in vector calculus. I think there is some intuitive kind of reason why we need these three operators to kind of take me from scalar to vector, from vector to scalar, and from vector to vector, okay? And I guess there's a fourth one, which is the Laplacian operator, del squared, which takes me from scalar to scalar, okay? So I can kind of go from any of those quantities. Let's do this on an example. Let's say that my function f bar equals, I think I have an example here that I like. Let's say it equals x, y minus sine z or z and 1. Okay, so this is my f1, f2, and f3 components. And if you like, you can also write this as, x, y in the I direction minus sine z in the j direction plus 1 in the k direction. So I want you to be very comfortable going back and forth between this I, j, k coordinate notation and this kind of column vector notation. These are equivalent representations. This is usually what physicists use. This is usually kind of what I use, applied math, differential equations notation here, but they're completely equivalent. But because I'm using this notation for the curl, for the determinant of this thing, I want to show you how simple it is to go back and forth from ijk to column vectors. Okay, so we're literally going to compute this quantity, the curl of f, for this very specific f vector here. So I'm literally just going to swap out f1, f2, and f3 for these quantities here, which is x, y minus sine z and 1. Okay, good. And now we actually just go through the kind of algebra of computing this determinant. So I'm just going to remind you, I'm going to do it kind of quickly. The way we do it is, to compute this determinant, I basically take the I component times the determinant of this 2 by 2 subblock that's kind of opposite it. So that's partial y of 1 minus partial z of minus sine z. So in the I component, I have this little subdeterminant, which is 0 minus cosine of z, so plus cosine of z. I did that a little quickly, but you can confirm that this determinant is just cosine of z. Then I have, okay, so that was the first block plus I direction. Then I do minus the j direction, so we always alternate signs as we go along these kind of majors. So minus in the j direction, the determinant of the 2 by 2 subblock excluding this column. So that would be partial x of 1, which is 0, minus partial z of xy, which is also 0. So I have 0 in the j component. So there's nothing in the j direction of this curl. And then again, so plus I minus j plus k, we alternate signs, plus in the k direction, we have the determinant of this 2 by 2 subblock. So partial x of sine z, again, that's 0, minus partial y of xy is just minus x. And so the curl of this vector field, is a function that is cos z in the I direction minus x in the k direction. And if you like, you can write that as a vector cos z 0 minus x. I'm sorry, my pen is squeaky. I know that drives everyone crazy. So really, really simple. This is how we compute the curl of any old vector field you like. You can write down any vector field you want, and it's relatively simple to compute its curl. Okay? Now, the interpretation of the curl is a little more subtle. What does this mean? What does it mean to have a curl that's cos z 0 minus x? And I'll talk about that right now. Okay, so let's now compute the curl on these simpler 2D vector fields. Okay, and so the way we're going to think about these 2D vector fields is essentially we have f1, f2, and 0. And so if you have f1, f2, and 0, then all of our curl is going to be in the k direction. Okay, and so I'm just going to kind of like write out what this would be in these cases. Okay. So let me do this in pink here. So if I want to compute the curl of a 2D f bar like this, I would say that in the I direction, it is oh my goodness, let me think. Yeah, I'm sorry, it's always in the k direction. And it's going to be partial f2 partial x minus partial f1 partial y, minus partial f1 partial y. This is the curl in 2D. This is just how you, and this is all in the unit normal k direction kind of going out of the board, the z direction that we haven't plotted here. This is x, this is y. We assume that this curl is kind of perpendicular to the board to be consistent with this notation. But this is the quantity we compute. So let's actually compute it here. Okay, so the curl of this vector field, curl of this particular vector field is partial f2 partial x, that's partial y partial x, that is 0, minus partial f1 partial y, which partial x partial y is also 0. And so this vector field is curl free. So we say that this is curl free or irrotational. Oh my goodness. Tational, probably 2 T's. Irrotational. Oh my goodness. I can't spell at all. Irrotational. So if the curl of a vector field is 0, it is curl-free or irrotational. I think that's probably spelled wrong. And this is an intuitive case. Okay, so this vector field is just, kind of radially sourcing out. It's symmetric. And if I have a particle that starts at some angle, it just blasts off in that same angle forever. It never kind of rotates around in this phase portrait. And so that's kind of the intuition of what it means to be curl-free. If there's no rotational component of this vector field, the vector field is said to be curl-free or irrotational. Okay, good. And of course, there's not 2 T's in here, because if I had just a regular rotational vector field, rotate is spelled with 1 T, rotational. Good. Okay. But this vector field down here, we have some reason to think that this is rotational, because again, if I start with a little particle or blob here, it rotates around this vector field. We've kind of seen that happen. So let's compute the curl of this guy here. Okay, so similarly, curl of f bar is partial of the second component with respect to x minus partial of the first component with respect to y. So partial of the second component with respect to x is 1, minus partial of the first component with respect to y is minus minus 1, which is plus 1, equals 2. So this vector field has a curl of 2, or it is rotational. So this is rotational. It is a rotational vector field. And I picked a really easy case where this vector field was divergence-free and had rotation. This vector field was rotation-free but had a divergence. You can have vector fields that have a little bit of both, that are kind of swirling and expanding. That would be like an unstable spiral source. Or I could have a vector field that's spiraling in, and so that would be a negative divergence, negative curl kind of situation. Okay, so this hopefully gives you an idea of the intuition of what this curl means intuitively on these vector fields. What else do I want to tell you? Okay, so this had a positive curl because this follows the right-hand rule. This vector field is curling with my right hand where my thumb is sticking in the positive out-of-board direction. This is just the convention we've agreed on. This is a positive 2 curl. If I had a vector field that was going the other direction, that literally I just said this was, I guess, like minus x and plus y, then this would be going the other way, and my thumb would be going into the board. That would be a negative 2. That would be rotating in the negative direction using the right-hand rule. So this is just a convention that we all agree on. I think it's a bit prejudiced. I'm left-handed, but I'm forced to live in a right-handed curl world. That's OK. Just get used to the convention here. OK, good. So we know how to compute this thing for generic, arbitrary, nasty 3-component vector fields, and we get our own curl vector field out. So that's kind of interesting. We also know how to compute it for 2D vector fields. You basically just look at the kth component and that little 2 by 2 subblock. here. Now, I want to give you a little more intuition for how you can use this curl. So maybe I'll just do it right here, and I'll show you how we can interpret curl for something like a solid body rotation. So this I think of as a fluid flow. Okay, this vector field is like the vector field that you would see if you looked at the Gulf of Mexico, or if you turned on your faucet in your sink or in your bathtub. You might get a vector field on the bottom metal pan, everything's spreading out. And so these are vector fields that are very intuitive from a fluids perspective. But what I want to show you is that you can also think about this for things like if I have an asteroid that's rotating in space, that also has an interpretation with the curl. Okay, so let me just finish this and show you how that situation looks. Okay. So how do I want to draw this? I am going to draw an asteroid or some just object. This is just some three-dimensional object. And it lives in x, y, z coordinates. So there's some coordinate system x, y, and z or z. And again, we're using the right-hand rule notation so that if I curl from x to y, my thumb sticks up in the z direction. Good. And what we're going to do is assume that this asteroid is spinning about some axis. And I'm going to make it really easy and say that it's spinning about the z or z axis. So we're going to define this w vector to be the vector around which this object is spinning. And we're going to say that it is rotating at a rate given by omega. And I know that my w and my omega look identical. But this little arrow tells you that this is a vector, and this doesn't have an arrow, it's a scalar. This is the angular rate rotating about this vector w. And in general, this vector w could be pointing any which way you like. I'm just picking it aligned with z because it's easier for me. Okay? Good. Now, a physical intuitive interpretation of curl is that if I have some point on this asteroid, or inside the asteroid, let's say I have some point, I'm going to call it Q, and literally from the origin to Q is a vector. So every point in this asteroid has some vector Q from the origin to that point. Then that point is moving at some velocity because the whole thing's rotating. So this is moving at some velocity that's kind of, perpendicular. It's kind of moving in the direction tangent to this rotation around this W axis. So this has some V vector of motion. This Q point has some V motion that's induced by this whole object rotating. Okay? And I'm going to say that this point Q is given by a radial vector r from the origin. So Q is defined as some r vector from the origin, and it is rotating. It is the rate of change of this is another vector v. And so the physical interpretation of curl that you've probably all learned in your physics class or in your calculus class is that this vector v is equal to my omega vector cross product with my r vector. So every single point on this asteroid, I define that r vector from the origin to that point. And to figure out what the velocity of that point is, I just take the curl of the vector I'm rotating about with that vector that defines that position. This is the velocity of every position r that's rotating about that axis w. So this is pretty cool. This is a useful interpretation of the curl, where essentially this is the angular velocity vector. So I'm just actually going to write that. So this is the angular velocity vector. Okay, good. And so if we have, so now let me write, assume that this w vector, if this w vector is just omega in the k direction, in the z direction, kind of in the z third component. If omega is just rotating at some constant rate omega in the z direction, and if we say and r equals x in the I direction plus y in the j direction plus z in the k direction. That's just how we specify the x, y, and z coordinates of this point Q. X in the I direction, I'll take x steps in the I direction, y steps in the j direction, and z steps in the k direction. That defines Q. then I can compute this v by taking the cross product of these two things. Good. And so v equals the curl of these two objects. And if I want to do that, I'm just going to leave this as an exercise for you all. You can compute this yourself. You get essentially w cross r equals minus omega y in the I direction plus omega x in the j direction. And this makes sense because if I have some point that is aligned with this axis in the k direction, that point's actually not moving. It has a zero velocity because it's just kind of spinning around its axis. It's not actually moving, with a non-zero velocity. So it makes sense that this curl, if I'm rotating about the z-axis, would only have components in the I and j coordinates. But this is where it gets really interesting, is that if we take the curl, so this v object, this v is a vector field. It is literally a vector field. Every point on this asteroid now defines a vector of how fast that point on the asteroid is moving around as this thing spins. So for every point, points that are closer to the axis of rotation are moving less fast. Points that are farther from the axis of rotation are moving more fast. Points that are at the very tips are moving the fastest. And that establishes this vector field for how this thing is rotating. Now you could actually convert this to radial coordinates, to cylindrical coordinates, and you would find that this does not depend on theta, but it only depends on the radius from that axis of rotation. So again, something you should do as an exercise. But it gets really interesting. So if I take the curl of this vector field, so curl of v is equal to, I have the I vector, the j vector, and the k vector. And I have partial x, partial y, partial z. And now I have minus omega y plus omega x and 0. Because that's literally what you're going to derive as a homework problem, is that this is the v vector. Then the curl of that we can compute pretty easily. Okay, so in the I direction, partial y of 0 is 0. Partial z of xy is 0. So this is 0 in the I direction. Similarly, in the j direction, partial x of 0 is 0. Partial z of omega y is 0. So plus 0 in the j direction. And now in the k direction, I have partial x of omega x, that's an omega, minus partial y of minus omega y is another plus omega. So I get plus 2 omega in the k direction. And so what this means is that if I have a solid body rotation, literally the rotation of a solid body, like an asteroid, of angular rate omega about some axis, like the k direction or the z axis, the curl of the vector field of all of those particles is equal to 2 times that angular rate about the axis of rotation. And so if I had been rotating about a different axis, this would be in that direction of that other axis. Okay? So that's a really powerful, intuitive definition of curl, is that a positive constant curl, this is just a constant, this is not a function of x, y, and z, it's a constant in the k direction. A constant positive curl is associated with a solid body rotation. Literally, like the geometry of this body doesn't deform or change as it's rotating. And similarly here, because I had a constant curl in this vector field, this also corresponds to solid body rotation. If I have some little blob or some object in this flow, it won't get deformed as it's moving around. It will keep its shape and just rotate as if it was a solid body in this fluid flow. So very, very useful concept here of solid body rotation. Okay, I realize that I'm just massively running out of time here, and I don't want to overload you, but a couple of last things I'll tell you. Really important facts. The curl of a gradient always equals 0. So the curl of the gradient of any f equals 0 for all f. Very interesting fact. So these are called potential flow solutions, these potential flow vector fields. any potential flow vector field is irrotational. So the gravitational vector field on Earth is a potential field. This is literally the gradient of the gravitational potential. That is an irrotational vector field. Things are just coming in at a constant rate. And if you come in at some angle, you'll stay on that approach vector. So the curl of a gradient is always 0. And similarly, the divergence of a curl is always 0. Div of curl equals 0. So the divergence of the curl of any vector valued function f equals 0, again, for all f. And this is kind of cool. If I have a vector field and I compute its curl, the curl of a vector field gives me exactly the components of that vector field that are rotating. So if this vector field had a divergence component and a curl component, if it was swirling and expanding, the curl would only pull out the swirling part of that vector field. It would only pull out the rotational part, and it would always have a divergence-free vector field. The curl of any vector field is always divergence-free. So we'll revisit these later. Maybe we'll even derive these, but I just wanted to throw these up here. Very, very important properties of the curl as they relate to the gradient and the divergence of a vector field. OK, good. So now we've covered the gradient, the divergence, and the curl. We're ready to start looking at how we would write down conservation laws in a control volume and starting to derive partial differential equations for real physical systems. So that's all coming up soon. Thank you.